Yes. Oh well, okay. So a question that was asked is, okay. So my control source is I know. I mean, let's say the control source is not ideal. So let's say I have a voltage controlled current source like this. So this is in N. So let's call this R in. This is A. This is A prime. B prime. GM. BA. Okay. So any comments on what I should do in the inter-reciprocal network? Very good, right? Remember, this is still an ideal control source, correct? So only you need to flip the controlled source and leave all the other non-idealities. I mean, a non-ideal control source is simply an ideal control source with some resistors, here and there, right? So all that you need to do is to flip so this will be Rn, this will be Gm times Vb hat, and this will be Vb. Is that clear? So, okay. So the inter-reciprocal network, therefore, is a way of exploiting reciprocity that works in all practical situations. And how many of you you've used SPICE before, or some form of SPICE? A big portion, right? So how many of you are familiar with noise analysis before? Don't be shy. I mean, it's okay if you've done it before, right? So you know that if you've not done it, you will get to learn it in this course. But those of you familiar with noise analysis, you know that you can click or you can find the contributions from individual noise sources to the output, right? And that entails finding the transfer functions from individual noise sources to the output, and that's all done. It's not it's not any more expensive to do that. It's just simply found using the inter-reciprocal network. And when we go a little further, I'll show you that, or we will see together that when we write down the matrices for, when circuits are all, as you know, on a computer, also all solved using matrix techniques, it just turns out to be a trivial transformation of that matrix, right, of the circuit matrices, and therefore this is routinely used in SPICE. Every time you run a SPICE simulation, noise analysis, it's used. Some of you may also be aware of a less known feature of SPICE, namely transfer function analysis, right? How many of you are aware of the AC analysis? Everybody is aware. And what does the AC analysis do? You have how many inputs and how many outputs? You have one input, and you can click on any node and find the frequency response from that one input to the output, correct? Okay. The transfer function analysis is the same thing done upside down. You choose the output port, and you can click on any independent source inside the network, and it will show you the frequency response from that independent source to the single output, and that's done again using the inter-reciprocal, right? And there is also another name for the inter-reciprocal network, inter-reciprocal. 'Reciprocal network'. 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 'R and that is it's also called the adjoint network. Right, and there is a good reason for this, as again we will see a few lectures down the line. Right, at this point these are just two terms that you need to be familiar with. Is that clear, people? Very good. Okay, so let me we have done enough derivation. Let's kind of see this in action, right? And a small example, and a slight extension of this, as and you'll be immediately able to see the point. For example, when you do an analog circuits course, what is the other element that you keep seeing all the time? You have the 4 controlled sources, say resistors, capacitors, inductors. There's something we spend a whole course deriving, the ideal op amp, right? So in N, let's say you had an ideal op amp. All right, and if you have an ideal op amp, what comment can we make about the properties of an ideal op amp? The gain is in, they're all the, yeah, of course, but when you embed an ideal op amp inside a circuit, what comment can we make about the terminal voltages and currents? So basically, yes, anybody else? If you have an ideal op amp, right, embedded inside a circuit, what do you do to analyze when you analyze the circuit? So what constraints does that the ideal op amp put? VA must be equal to VA prime. Okay. Okay, and IA equal to 0, and what comment can we make about VB? Well, VB is dictated by the circuit, right? Okay, and under what conditions are these valid? The most important thing to realize is that this is negative feedback, or rather DC negative feedback. Around the op amp. Alright. Okay. So in N, if you had an op amp, ideal op amp, what comment can you make about what you should do in the adjoint network? What kind of control source can you think of an op amp as? Actually, it's not necessary to think of it as a voltage controlled voltage source with infinite gain. You can think of it as a voltage controlled current source with an infinite transconductance, or a current controlled voltage source with infinite transimpedance, or a current controlled current source with infinite gain, right? As the controlling parameter tends to infinity, right? And what is the intuition behind any of those assumptions? Remember, if you have a control source which is embedded inside a circuit and the circuit is working, all voltages and currents must be finite, correct? So if this controlling parameter happens to be infinite, okay, and the voltage between B and B prime is finite and mu is infinite, what comment can you make about VA? Should be 0. Okay. Likewise, if the controlling parameter Z is infinite, and the current passing through the branch, I mean the voltage between B and B prime is finite, what comment can you make about A and A prime, the voltage between A and A prime? The voltage between A and A prime in the current control voltage source is anyway 0. What comment can you make about the current? Is also 0, right? And likewise with a voltage controlled current source, if this current is finite and GM is infinite, okay, it's easy to see that, well, the difference between A and A prime is, the voltage difference between A and A prime is 0, correct? So, all that I would like to point out is that it is not necessary for us to think of an ideal op amp as simply a voltage controlled voltage source with infinite gain. You can think of it as any one of those 4 control sources with that controlling parameter tending to infinity, right. Now, with that reasoning, what comment can you make about the ideal op amp? If you want to replace the ideal op amp if the original network consisted of an ideal op amp, what could we replace it with in the adjoint? Ideal op amp with what distinction? Remember, an ideal op amp is slightly different from an ideal control source in the sense that the controlling ports, terminals are both available, right. So, this is VA, and let us say if I assume this to be a voltage controlled voltage source, this is mu times VA. But what comment can we make about the ideal op amp? Well, from the picture you see that it is only B which is accessible. What is happening to what is happening to B prime? B prime is internal to the op amp and is therefore not accessible. It is a ground, but it is internal to the op amp and not accessible. So, this is B. All right. Now, if you want to form the adjoint, if you had something like this, what would it? Let's do it step by step. What comment can you make if you make this in the adjoint network? How would this look like? So, current controlled current source. The controlling port must have one terminal grounded, correct. So, this is therefore IB hat, okay. Let me just change the signs to B, okay. And what must be the controlled port? This is a voltage controlled voltage source for the original network. So, what did we say for the current controlled current source? What must be the sense of the current? Going up or coming down? Going up. So, this is A prime, and this is mu times IB. Is that clear? And therefore, now we say, well, this is an ideal op amp. So, what must mu tend to? Mu must tend to infinity, right? Okay. So, mu must tend to infinity. So, even though the original circuit had, the original op amp had both the input terminals accessible, but one output terminal not accessible. So, in the inter-reciprocal network, what else will, what do you see? Well, both the output terminals are accessible, but only one input terminal is accessible. So, this is A and this is A prime, and this is B. all right. So, let us take an example. So, this is n hat. Let us take a simple example to illustrate the point. Let me take in fact a trivial example that all of you are very familiar with. Let us call this so, what is the problem? What would we like to do? Find transfer functions from V out to, from V1, V2 and V3 to V out. Okay. I mean, this is a pretty straightforward example. You do not really need the adjoint concept to go and do this, but it's just, as I said, to illustrate the point. In reality, you have much more complicated networks, and therefore, the adjoint is used de facto. So, help me, this is n. So, the first step is to draw n hat. So, what are we going to replace the op amp by? In this network, it just incidentally turns out that one port of the the input port of the op amp has also one terminal grounded, right. The output terminal is, the output port anyway has only one terminal accessible, right. Now, what do? So, we draw the adjoint. So, we have V1 which is 0, right. So, this is a voltage source, this is R1, this is V2, this is V3, this is R2, right. The only controlled source is the op amp. What are we supposed to do now? Yes, Alfred. Very good. So, as Alfred suggested, we are going to do this. Okay, and this is the output. Okay. So, first part of the job is done. We have found the adjoint network or the inter-reciprocal network. What is the next thing to do? We need to find the voltage transfer functions . So, we need V out by V1, V2, V3. Okay. So, what do you suggest now that we do? We exploit reciprocity. What do? The voltage transfer functions in the original network now become current transfer functions in the reciprocal or the inter-reciprocal network, right. So, what do you suggest that I do? Excite it with a current source I, or let me call that I hat, alright. So, now this is standard circuit analysis. Where does all that I flow? What is this potential, by the way? This is the virtual ground of the op amp, that is 0. So, where does I hat flow? right. So, this is I hat, alright, and what is this voltage? Come on people, minus I hat R2, correct, and therefore what comment can you make about this current? Yes, what is that current? You know the voltage here, I mean can somebody tell me what that current is? Remember all these voltage sources are, I mean these are just names, right, they are all 0 voltage sources because we need to find the currents through them, correct, okay. So, what is the current through R1? Minus I hat R2 by R1. Okay. And therefore, what comment can you make about V3 by, so what comment can we make about V out by V3 in the original network? It is simply the same as please think carefully and be careful about the signs SIGNS. What is the direction of the current through the voltage source V3? So, V out by V3 in the original network is what in the inter-reciprocal network? What do we need to do? What is it? I am not looking for the answer. What is the input and what is the output we are looking at? Yeah, the current into the positive terminal of V3 is our output quantity, right. So, that is the current flowing into the positive terminal of V3 is minus I hat. So, that is basically minus I hat divided by I hat, which therefore is minus 1, correct, okay. And likewise, what comment can you make about V out by V2 in the original network? What is the output we are looking at? We need to find the current flowing through the positive terminal of V2 in the inter-reciprocal network, and that happens to be minus I hat times R2 by R1, that divided by this must be minus R2 by R1, and it is evident that the current flowing through V2 and the current flowing through V1 are the same, and therefore, this must also be equal to V out by V. Alright. So, in one shot, I mean we have found all the 3 transfer functions, right, but if we did not know this adjoint concept, what we would probably have done is, assume these two do not exist, and what is the transfer function from V1 to V out? Minus R2 by R1, right, and then if you open your eyes carefully and see, then you would see that the transfer function V1 and V2 are in series, and therefore, there is no point in doing the analysis all over again. It is the transfer function from V1 to V out is the same as the transfer function from V2 to V out, and you say, oh well, that is also minus R2 by R1, right. from V3, what is the transfer function from V3 to V out in the original network? Well, you assume V1 and V2 to be 0. This potential, the virtual ground potential will be, well, you would say this is 0, okay, and this would be V out will be minus V, right, and that's fortunately also what's predicted by the function. Is that clear? So, to summarize, therefore, the concept of inter-reciprocity is basically a profoundly important one and is used all the time routinely used in circuit simulators. How many of you are aware of this before? I mean, I can understand the undergrads not seeing this, but yeah. So, as you can imagine, right, even experienced students here haven't seen this, right, and it's also quite strangely also not known to most circuit designers that you can use reciprocity with a small twist, and it's not some exotic thing that's only there in the textbooks. It's actually there routinely when you do SPICE on your circuits. This is what is being used. In fact, you will see going forward that's actually, as I was mentioning, it's almost a trivial manipulation of the matrices that allow us to do this, right? And as we'll see going forward later in this course, when we start talking about time varying circuits, you will find that the same concept is also used to derive a whole bunch of interesting stuff, right?